Close your eyes. Now open them. This reality you're perceiving, is it being constructed because you are observing it? Is your consciousness the fundamental ingredient that breathes this world into existence? It sounds like a supernatural concept, a philosophical fantasy. So why did the founding fathers of quantum mechanics, the architects of the most successful scientific theory in human history, seriously entertain this exact idea? Did these brilliant scientists make a fundamental mistake? To find out, we have to go back to the beginning of this entire controversy. Back to history's most powerful and most miraculous experiment. The double-slit experiment. You may have heard of it, but very few understand its true, devastating implications. Today, we will burn its correct interpretation into your mind once and for all, because it is the backbone of quantum theory, and it proves that reality, the world around us, the things we see and touch, is in a very real sense an illusion, just as the fathers of quantum theory believed. A few centuries ago, physics was in chaos. The greatest minds were locked in a bitter war over a simple question. What is light? Is it a particle or is it a wave? In science, experiments are the ultimate authority, and the experimental evidence was utterly contradictory. Light was simultaneously behaving like a particle and a wave. It was as if a single coin was showing both heads and tails at the same time. One physicist would prove one ball was blue. Another would perform a different experiment, look at the same ball and prove it was red. How can one thing have two mutually exclusive natures? To solve this, we need to see what the scientists actually saw. In the 17th century, two factions emerged. Group A, the Newtonians, believed light was a particle. Group B, led by Christian Huygens, believed it was a wave. Both had solid evidence. Newton was a titan. So for the next 100 years, his particle theory dominated mainstream physics. But his claim began to crumble in the early 19th century. Two experiments, back-to-back, delivered a knockout punch for the wave theory. First, in 1804, Thomas Young's double-slit experiment showcased light's destructive interference pattern. Then in 1819, François Arago demonstrated constructive interference with his Poisson's spot experiment. This interference, the merging and canceling out of waves, is a signature property of waves. It cannot be done by particles. With a score of 2-0, Huygens' wave theory ruled physics for the next century. But the game wasn't over. The 20th century arrived, and with it, two new experiments that resurrected Newton's particle theory from the grave. First, in 1905, Einstein's photoelectric effect showed that light, in the form of particles, knocks electrons out of their atoms, an interaction that requires a particle. Second, in 1923, Arthur Compton's scattering experiment showed that X-ray light collides with electrons and transfers its energy to them, again, a particle-like behavior. The score was now tied, 2-2. A tiebreaker was needed. For years, physicists searched for it, but it was nowhere to be found. The evidence from both sides was impeccable, repeatable, and undeniable. Finally, they had to collectively surrender to a bizarre new truth. Light is dual. It exists in nature as both a particle and a wave, simultaneously.
This was a monumental turning point. The first chapter of physics, defining reality, was over. The second chapter, understanding matter itself, had begun. They understood light's duality. But then a revolutionary thought emerged, a thought from the French physicist Louis de Broglie. If light can show wave-particle duality, then why can't matter? What crime have electrons, quarks, and atoms committed? Brilliant. In 1927, Clinton Davison and Lester Germer tested this hypothesis. Their famous experiment proved it. It doesn't matter if it's light or matter. At the quantum level, everything behaves like a wave. I want you to truly appreciate the bomb that just detonated in the minds of these scientists. On one hand, you have the certain knowledge that you can touch and feel the objects around you. They are solid. On the other hand, experiments are now proving that all those solid things are actually made of waves. Waves that have no definite position, only a probability of existing somewhere. The implication was obvious. Perhaps the quantum world operates by these strange, wavy rules. But as we move from that microscopic realm to our macroscopic world, something happens. The waves somehow surrender their nature and transform into a definite, concrete reality. But no one knew how. This became the single biggest question in science for the next 100 years. So, how does this transformation happen? How does a probabilistic wave become a definite particle? Run your minds on that. The answer is coming. This conversion was so perplexing that many scientists turned to philosophy to digest it. But do not draw any conclusions yet. The story is not over. This is not the take-home message. Many of the founding fathers themselves misinterpreted this. While de Broglie's idea was confirmed, three giants of quantum physics, Niels Bohr, Erwin Schrödinger, and Werner Heisenberg, were unsatisfied. To study this wave nature, they invented mathematical formulas called the wavefunction. But Heisenberg and Bohr were obsessed with a deeper question. Schrödinger's equation describes the wave perfectly. So why and how does that wave collapse? Why don't we see it? After intense thought, they realized the answer might lie in the double-slit experiment itself. They proposed a new thought experiment. What if we place a detector at the slits? What if we watch the photons? Perhaps the very act of measurement, of observation, forces the wave to collapse into a particle. Because to measure something, you must interact with it. You shine a light on it. This idea, and all its variations, later became known as the Copenhagen Interpretation. From this, some very weird conclusions emerged. Even Einstein found this idea absurd. This is when he famously taunted Niels Bohr. Do you really believe the moon is not there when you are not looking at it? Einstein was a staunch opponent. He did not agree with Bohr, even though Bohr had mathematical backing. What was missing was the technology. They could not actually build the detector for the experiment. Think about that. You, today, have the opportunity to understand quantum mechanics more accurately than its own founders. Heisenberg, Bohr, and Schrödinger died confused by their own theory. But you will not. The updated experiment was finally performed in 1970 by the German physicist H. Dieter Zeh. He did the double-slit experiment in real life with a real detector. Zeh, and similar experiments in the 80s,
all pointed to one clear physical explanation. The confusion is created by three words: wave function collapse. If we replace that term with quantum decoherence, everything becomes crystal clear. Let's rewind. In 1926, when Schrödinger created his equation, a physicist named Max Born invented the Born rule to interpret it. He said the interference pattern on the screen doesn't mean particles are a fluid. It means all the particles from the beam are propagating in perfect sync like a marching band, and we can use math to predict where they'll most likely hit. Now, what happens when we place a detector at one slit? That detector shoots photons at the particles to get a reading. But this method has a fundamental flaw, a flaw you probably missed, but not today. This flaw is the hero of our story. Its name is quantum decoherence. Decoherence simply means the breaking of sync. When the detector's photons randomly collide with our quantum particles, two things happen. First, their perfectly coordinated path is disturbed. They get knocked off course. Second, the collision transfers energy, changing the frequency of those particles. They are now out of sync with the particles from the other slit. Their rhythm is broken. So, the beautiful in-sync wave interference pattern is ruined. We see a messy, non-interference pattern instead. First, we saw a spread-out wave pattern. Now, we see localized hits. And what is a particle? It's localized energy. And there it is, your wave-to-particle conversion, quantum decoherence. But why do quantum objects behave like waves while large objects do not? The answer again is decoherence. Imagine a totally empty space. You shoot in photons, electrons, and quarks. Every particle has its own wave function, its own rhythm. Two things happen. First, they start entangling, sharing their wave functions. Second, through countless interactions, their perfect sync is shattered. They fall out of rhythm. Imagine hundreds of thousands of people doing the wave in a stadium in perfect unison. That's coherence. Now, push a few of them. Their rhythm breaks. Soon the entire wave falls apart. That is decoherence. When the wave functions of a system become desynchronized, their values mathematically cancel each other out, and a single, net, particle-like output emerges. This is why large objects never appear wavy. A tennis ball has 10 quadrillion atoms. The chance of all their wave functions vibrating in perfect, undisturbed sync is 0. It's like starting a million clocks and then constantly disturbing them. They will never all show the same time. That's why large objects always show particle properties. Their wave nature has averaged out into a particle due to decoherence. In principle, if you could somehow bring all 10 quadrillion atoms of a tennis ball into perfect, unified sync, it would start showing wave properties. Scientists have actually done this with molecules containing hundreds of atoms, but for a tennis ball, it's practically impossible. And even if you did, another restriction kicks in, the de Broglie wavelength. The equation is wavelength equals h divided by mv. This means as mass increases, the wavelength shrinks. For a tennis ball, the wavelength becomes 10 to the power of -33 meters.
That's the size close to Planck length. You could never, ever notice it.
These are the universe's built-in barriers, the majestic restrictions that forever separate the quantum world from our classical world. And now you know. Whether you call it wave function collapse or quantum decoherence, it is a purely physical, logical process. Scientists understand this so well, they've performed recoherence experiments. They caused decoherence, watched the waves become particles, and then made them coherent waves again. Mind-blowing. What do you guys think? Let me know in the comments. And as always, don't forget to like and subscribe to Brainwave. Until the next time, take care.